Okay, this is a, a video on 6.1b, where first we start with a little recap of what we did in 6.1a, which was basically talk about what a random variable is, which is a range of values based on a random event. And random variables can be discrete, which is what we touched on last class, where they take on specific values. Whereas a continuous random variable that we'll talk about today has infinite numerical values, either within a finite range or in an infinite range. And when you think about a discrete random variable, it's something you could count, like number of kids in a family or number of calls you get per day. Whereas when you talk about continuous random variable, we really think about things that are measured, like the miles per hour someone runs the 1 mile race, or the distance from school, things that could be measured. And, you know, the distance from school, yeah, most people just round and say 10 miles, but it really could be 10.123456 miles. All right, so let's start with this first one, which is a review of what we did about discrete. And with discrete, you, again, have the values that the random variable takes on. In this case, we're talking about number of repair calls appliance shop receives in an hour. And it can be 0, 1, 2, or 3. And then the probability of achieving of each of what's the probability that each of those will occur. And so when we talk about what the expected value is, well, that's our mean. And this mu of x, that looks kind of like a weird U, stands for population mean. So instead of a sample, we're using this to describe the mean of a particular population. So, and in order to find that mean, we're doing the expected value, which is really like a weighted average. And to do that, so in this case, our mu of x, you take each of the data points, and this is for discrete, and you multiply it by its probability. So 0 times 0.1 plus 1 times 0.3 plus 2 times 0.4 and plus 3 times 0.2. And we end up getting there 1.7, which means the mean number or expected value number of calls per hour is 1.7 calls. And then it's often helpful to enter these into our calculator. And to do that, you would have L1 be your repair calls, and then L2, the frequency, is going to be your probability. And if we do a little graph, you're going to see, and you can check out my solutions, that it's roughly symmetric, maybe slightly skewed left. And then thinking about, all right, so if we knew on average 1.7 calls per hour, how could we then use that to say in a typical 8-hour day, how many calls do we expect? Well, on average, we would then expect 1.7 times 8, or 13.6 calls in an 8-hour day. So that was the expected value piece. Again, expected value being that population mean, mu of x. Well, now, as you know, when we're talking about a variable and its distribution, the measure of center, which we just found, that mean is important, but also the measure of variability is important, or the, and in this case, we're going to use standard deviation. And we're going to use that expected value we just had to help us find the standard deviation. And first, you usually find what's called the variance, which is the standard deviation squared. And then to get the standard deviation, you're just going to do the square root. So the symbol for the standard deviation of a population is this lowercase sigma of x, versus when we talked about a sample, it was s of x. And then it's going to be just like we did with standard deviation back in the first semester. You want to do the difference between your data point, the first data point is 0, and the mean, which we just found to be 1.7. You square that, but instead of doing that for every point and just adding it together, you want to weight it, because each one has a different probability in this particular case, so you'd multiply this by 0.1. Then you would do the same for one call, minus the mean squared times that probability. Then plus 2 minus 1.7 squared times the probability associated with that, plus 3 times the mean squared times the probability associated with that. And that, again, I should have put a squared here. This is going to give you the standard deviation squared, or the variance, which ends up being 0.81. And so now, just to find the standard deviation, we're just going to take the square root of that. So the square root of 0.81, which is 0.9 calls per hour. So on average, the number of calls per hour differs from the mean by 0.9 calls. All right, C is a bit of an extension, and kind of for the AP folks to think about, typical type of question they might ask. In an 8-hour day, would it be unusual for the shop to receive only 5 calls? Justify. All right, so we want to use the standard deviation, and we want to use the expected value to see if this is weird. So one thing that we might do is figure out if there were 5 calls in an 8-hour day, what does that mean about calls per hour? So 5 calls per 8 hours. That's gonna, when we do this on our calculator, it's about 0.625 calls per hour. So remember what the expected value was. The expected value was 1.7. So let's see what the difference is between what we have here and our expected value. So if I do 0.625 minus our expected value, well, the difference there is negative 1.075. Okay, so they differ by 1 in some calls. Well, let's see how that relates to the standard deviation. So if I divide negative 1.075 by my standard deviation, I'm getting negative 1.19. So in other words, what this is telling me is if we got only 5 calls in an 8-hour day, this is really 1.19 standard deviations below the mean. So it's more than a standard deviation away from the mean. So I might say it's not a unheard of type of day, but maybe I would say it's unusual because it's more than 1 standard deviation away from the mean. So it seems like an unusually slow call day. All right, so that's going to be part 1 here, is the opener. So now that we've done that, in video 2, I'll talk about, we're going to start talking about the distribution of continuous random variables and how to deal with probability of continuous random variables.